Hello, I'm Paul Downing, and today I'm going to be talking about the importance of workflow techniques as applied to blockchains. Workflow is one of the most important things that you have to consider when designing or reviewing a process or a computer program. And in this short video, we'll show how those techniques can be applied to current blockchains and how we used it in our own design, our own distributed ledger protocol, Tapestry X.
So let's consider the Bitcoin network with its validation method known as proof of work. There's the blockchain, and all the participants have a copy of that blockchain. In this case, participant A creates a transaction, and although this is a simplified version of what happens, the transaction gets propagated in the network. Another participant has a transaction, and that transaction is propagated to the network too. And this continues until there's enough transactions propagated in the network that the miners can create a block, and they then compete to solve the puzzle of creating a hash that's below the level of difficulty in the network. And the first one to do so creates the block that goes on the blockchain and propagates that block in the network. And then everybody can update their copy of the blockchain. Now that looks all fairly simple, except because of the size of the Bitcoin network and the latency in the processing of blocks, another miner may have created a block, which then creates what's called a fork in the network. Effectively, this is now two possible directions the chain can go in, so there's a question mark on which block should be hashed to next. And in fact, the miners may be competing in different parts of the network to do that. But in this case, we'll assume that the green block is the one that has the longest blockchain and the blue fork is dropped. In this case, though, you have to wait until you're 6 blocks from the end of the blockchain to be sure that another fork won't occur and eliminate your block with your transactions. So before you can respend Bitcoin, you should normally wait till you're 6 blocks into the chain. Now, when we're looking at the process, you can see that this is slow and also arbitrary in terms of time, because although the blocks are created every 10 minutes, you're not guaranteed to have your transaction in it. There's also an unscalable finite capacity, because there's a finite number of transactions that can be created within one block within every 10 minutes on average. There's a finite capacity. So if the capacity of the block creation is exceeded by the network, there will be backlogs. There's also an unscalable active memory, because you have to keep the entire blockchain from the genesis block until the current block in active memory, and it's only getting bigger.
Now, considering consensus algorithms in blockchain networks, you have the blockchain, and let's assume everyone has a copy. As a participant creates a transaction, it's disseminated to the network. But now, each participant not involved in the transaction has to review the transaction and vote on it. And those votes are then disseminated to the other participants. So node A votes and passes it to everybody. Node C votes and passes it to everybody. Node D votes and passes it to everybody. Node E, Node F, and Node G. Now, the important thing to point out in this flow, although a lot of these things can happen in parallel and overlapping, all this activity is just for one transaction. So imagine now there's been multiple transactions and multiple votes. Each of the participants then are able to assemble a block based on the votes and the ordering services and add it to their copy of the blockchain. But what we haven't shown here in this flow, and it's fairly intense and involved, is obviously the multiple transactions, a block ordering service, how the actual votes are ordered to be hashed in the correct order. There's federated solutions that rely on elections for the ordering service or random selection of them. So that process wasn't included. And we haven't shown the sort of cross-network latency in terms of how these various things are accomplished, or if the network includes shards or clusters or channels, depending on the protocol, the latency of transacting between those shards and clusters. The process is still slow and arbitrary because you have to get all these transactions and all these votes assembled. And increased participation actually increases the latency. Obviously, the more participants and more votes there are, it's going to take longer. We still have the unscalable active memory problem that we mentioned again in Bitcoin, because you have to keep the entire blockchain in active memory. And then the other final thing, which is a little bit counterintuitive, but it's true, that computationally, this process is unscalable, because as the number of participants and number of transactions goes up, that actually increases and scales exponentially. So these networks have a habit of becoming slower as they get bigger. So you can see, by applying workflow techniques, it allows you to both critique and understand the different validation methodologies. And at L4S, we applied workflow to our design processes to ensure that we had an optimal design from the get-go. In this protocol for Tapestry X, a transaction is created by a participant and broadcast to the network. And all the other participants then just have to validate the transaction, post and reconcile it to the distributed ledger. It's that simple. Create, broadcast, validate, post and reconcile. Create, broadcast, validate, post and reconcile. So this is what we do. How we do it is part of our secret sauce. But what you can see is that it's linearly scalable, because the computation is related to the creation of transactions or the validation, post and reconciling. It's near real-time settlement, because as soon as transactions are posted, they're good. With this design, we believe we can get to over 100,000 transactions per second as a processing capacity throughput. And behind the scenes, we've also added double entry accounting. Now, the double entry accounting allows us to create payables and receivables. In other words, we can record obligations, not just transactions or transfers. And then, because we separated the transactions and the balances in the ledgers, as most ledgers do today, we're able to create transacting periods and archive the immutable history of our distributed ledger. But because we've got the concept for transacting period, we can actually record future dated transactions as well. And our system, through a certain mechanism, is interoperable with legacy processes as well as other networks. So what we have, in summary, is massively parallel processing with a self-synchronizing distributed ledger. Now, self-synchronizing may sound counterintuitive, but it's actually backed by academic research. So we have consistency and completeness of a distributed ledger without the need of consensus. Well, I hope you found that useful, and you can see how the application of workflow techniques allows us to both understand and critique other blockchain protocols, but also helped us in designing an optimal distributed ledger protocol. If you're interested in L4S and Tapestry X, please feel free to contact me on LinkedIn. Thank you.